Like some of not registered come and see us after during the tea break or after talk. Most of you have introduced yourselves to each other, so you know that you should ask questions. You know that you might be called upon to use your clickers, and you know that the scheme works in such a way that there are some introductory lectures covering the basics before we turbo boost into advanced cutting-edge physics from there, sort of cutting-edge in any case. So this morning, Mark, who introduced himself yesterday, will be starting his series of talks on the hard science.
Thanks very much, Christian. Good morning. Thanks for coming. So today I just want to give you through a few examples, vignettes, some of the sort of characteristics of soft matter. So this is the idea, and as Christian said, feel free to interrupt with questions. So some of the ideas that occur in soft matter that I want to illustrate with examples, and then as we go through the examples, I'll try to reiterate at the end which of these features the examples illustrate are the following. Okay. Soft means something is easily deformable. So, in particular, that means can often change its shape, exhibit a wide variety of shapes. I sometimes like to give a little bit of dig to the cosmologist here, because at the very largest scale, it turns out the universe is spatially flat. One might have hoped that it had some nice, interesting, large-scale curvature spatially, but it doesn't appear to. It appears to be completely flat, and it doesn't even have interesting topology. In soft matter, by virtue of these easy deformations it can take, we see all over the place rich geometries and topologies. For cosmology, of course, we're talking strictly about spatial curvature. There's space-time curvature in cosmology, that gives you Einstein's equations and nice behavior of matter flowing through curved spaces and so on. But here, we're going to get interesting spatial structures. Another crucial feature of soft matter is that systems can exhibit multiple kind of phases. The kind of phase a system exhibits can depend on the length scale and the time scale at which you probe it. So, our simple notion of being in some kind of organized phase of matter is solid, a liquid. You'll see liquid crystals here a lot in this 2 weeks. Magnetic phases, superconducting phases, all of this stuff has to be generally qualified with the statement of, okay, over what length scale are you examining it? There are short length scales, mesoscopic length scale, very large length scale, and over what time scale are you probing it? The phase that you're in can depend on both of these things, which means the system can exhibit multiple phases. It might be liquid if you deform it very slowly, and solid if you try to deform it rapidly. So this means you take phase diagrams, which are already very rich. Right? I mean, when I went to school, there were 3 or maybe 4 phases of matter, and there are literally hundreds of them now. But then we have to move across that phase diagram spatially and temporally. So the complexity and the richness is just enormous by virtue of the flexibility of some of these soft systems. Another feature is that these systems can be extremely sensitive. There can be extreme responses to very small changes. We'll see an example of that. So this gives you the ability to sort of configure matter. You go in, make some little change, and that can have a macroscopic consequence. By virtue of being easily deformable, this means, you know, when you first study things like the Gibbs free energy, F. This F has an internal energy piece, U, and has an entropic piece, TS. And they come with also a relative minus sign, U minus TS. In hard systems, typically they're dominated by this internal energy piece, and you're minimizing energies. But when a system can assume lots and lots of configurations, then the entropy part becomes important, and it can even dominate. So entropic dominance, or the role of entropy, is often very, very important in soft systems. And even at zero temperature, soft systems can be unusual by virtue of the configurations they can explore or attain, and I call that unusual ground states. Okay. So there are quite a few things here, and everyone working in the field would probably make their own list, but here's some that I like, and I'll try to give examples of these and then come back and tell you which feature here is exhibited by that system. So the plan is 5 vignettes of soft matter. First I call the Amazon boot and Mr. Bouvier. Then I'll talk about polymers, some of you are working on, in particular heating polymers, so the role of temperature and polymer response to temperature. I'll talk about two-dimensional extended objects, namely membranes that can change their shape. And I'll talk about two, you could say, universality classes of membranes, fluid membranes and elastic membranes. And if I get a chance at the very end, I'll mention something that where a liquid-like system can exhibit hard-like structures typical of crystalline-like systems, namely faceted structures. And this will be something I'll talk about late at the end of my talks, series of talks. So that's not all of the stuff you'll have all of the background for, but you should be able to see the basic story, and you'll get more background as 2 weeks go on to understand this. Okay, any questions so far? So, here's our first example. For a couple of thousand years, South American Indians have known the following fact. You take this tree, it's the Hevea tree, and you sample its sap. You collect the sap by doing a cut in this tree. So this is a liquid, milky-like liquid substance, and you can coat your feet with it. And then you let it dry. And after a while, it solidifies. And you have a boot. So this is a natural boot. So the transformation here is from a liquid to a solid. So how do we understand this trick today? The liquid is actually called latex. This is natural latex. So this is a polymer. The polymers will also enter here. So we have our basic objects are extended structures. That's important. And so you basically have their long chain molecules. They're sort of microscopic spaghetti. They're soft, flexible, consume. This is the easily deformable part. Flexible means it doesn't cost that much energy to assume a lot of interesting shapes. These are related. The scale is about 10 to the 5 times smaller than noodles, but the idea is the same. So you get something like this. Initially, these molecules can just kind of flow around each other. That's why they behave as a liquid. But you're exposing them to air, and this latex reacts a little bit with oxygen. So what happens is a few, and this is important, just a few of these chains get linked by reacting with oxygen. So they sort of you pin one to the other. And it only takes, so then you have a kind of a very, very loosely tied fishnet. Right? Most of the molecules are kind of flowing around, but every now and then one's pinned to the other. And that pinning links them all up, constrains the configurations enough that the thing is solid on a large length scale. That's your boot. So here's the initial structure, here's the final structure, and here I've grossly exaggerated these crosslinks, Curonian places. So what's unusual about this solid? It's solid at the macroscopic scale, but it's fluid at the microscopic scale. You can test this. Okay? You can do nuclear magnetic resonance imaging or MRI. You can put in molecules and see what's happening to things at the very microscopic scale. And there they swim around like fluids. But the pinning or cross-linking every now and then makes it macroscopically solid. So this is actually rubber. This is natural rubber. There's a downside. These boots last about 1 day. After a day, they disintegrate. And that's because oxygen is a little bit too reactive. Okay? After cross-linking, it starts attacking the system even further and eventually cleaves it, and your fishnet falls apart. So, around 1839, Goodyear is a chemist. Chemists, they like to do experiments. Like to try different things, see what happens. So he boiled this heavier latex with sulfur instead of oxygen. Sulfur's in the same column of the periodic table as oxygen, has many similar characteristics. It does this cross-linking, but it's not as reactive, so it doesn't do the final cleaving. So this gives you basically the rubber you use today, for example, in car tires and a million other places. So this is also a nice, moral of doing science. It's good to try things even if you don't know the outcome. In fact, if you know the outcome, it's rather boring. So that yields natural. Call it natural rubber. The sensitivity, only one in 200 or so carbon atoms reacts with the sulfur in the system. But that's enough. That tiny effect is enough to trigger phase transition in the system. So that's this feature here, extreme responses to small changes. And this exhibits both of them, extreme responses to small changes and multiple phases, microscopic liquid, macroscopic solid. Anyone else know another example? Have you, yeah?
You mean an example of salt matter?
Well, something that's solid and liquid.
And
You know, what
inside the cell.
in the cell?
Yeah, the
Okay.
gel.
Okay.
Inside the cytosol.
Cytoskeleton. Okay. Yeah, it's an extended network where the polymers are biofilaments. Right. In fact, biological systems that we'll have discussions about utilize these kinds of characteristics of soft matter quite a lot. Biological systems they're basically living in an aqueous-like environment, so that liquid-like character is important. But completely liquid things tend to be, a little bit too fragile. You need some structural integrity somehow. So it's kind of linking up to make something that has a little bit of rigidity, a little bit of solidity of macroscopic scales is utilized a lot in biological systems. Another simple one's cornstarch. Anyone ever done that experiment? You take cornstarch, you can do it in your kitchen, and you just dissolve it in a little bit of water, and you can just push your finger through it. If you make a big macroscopic pool of it, you can swim in cornstarch. But if you hit it, it's solid. It's basically like rubber. Bounce off it. And in fact, if you make a pool of it, you can walk across it. You can walk on water. And there, this is an example of the time scale at which you perturb it. When you move slowly, all the polymers can flow around each other. But if you try to move them, to form them too rapidly, an abrupt, fast deformation, they don't have time to rearrange, and they're quite solid. So you can go on YouTube, and there's a Barcelona television sort of comedian science commentator, and they all walk across these big vats of cornstarch, and then in the middle they go down like the Captain.
It would be an interesting effect if we put it on a loudspeaker or some kind of transponder.
And look at the look at the response. Rubber does it as well. It's interesting sound responses. Today I'm going to be talking about spontaneous symmetry breaking and the basic origin of topological defects, why they can occur, and some of their structure. So, one of the most profound ideas of the last century in physics was the idea of spontaneous symmetry breaking. So this is the idea that you can have a symmetry of a theory built into, say, the Hamiltonian or the Lagrangian or the action or the free energy, whatever the formulation that you take. But the ground state of the system, or the vacuum if you're talking about a field theory, may not realize all of the symmetries of the basic Hamiltonian. Some of the symmetry, it might have some symmetry, but not all of the symmetries. So some symmetries are in the theory, just not realized in the ground state. So you break symmetries in some way. Now, the consequence of this is that you have a certain, often, the ground state is not unique. There's more than one ground state. And in general, there's going to be a manifold of ground states. And that manifold can have some very rich structure, some interesting geometry. It's typically infinite dimensional manifold. And in particular, can have some interesting topology. And one of the consequences of non-trivial topology of the space of distinct ground states is topological defects. Now, this idea of spontaneous symmetry breaking, generating structure, is fun and interesting, rich, and quite counterintuitive because of this symmetry breaking that we call it. We're trained, particularly in physics, to exploit symmetries of problems in finding solutions. But this can lead you badly astray because of the symmetry breaking. And there's a kind of cute, discrete example of this that I would like to share with you. So this is the following. So this is called the opaque square problem. So we get our optics experts like Ivan, Hall, and all these people to give them the following problem. We have this is all two-dimensional flat space, nothing funny with curvature or anything like that. We take a square 1 by 1. And our objective is the following. We need to build a mirror that will block light that shines from one edge to any other edge on this square. And we are cheap. We want to build the mirror of minimal length. That's the key constraint. Minimal length mirror that will block light that goes from one edge to any other edge. So, of course, we could have a mirror. So a typical path of light will be from here to here. You can also imagine that there's a telephone line buried just below the ground, and you need to dig a minimal length trench that guarantees you'll uncover the telephone line. Different formulation of the same. Here's a typical path that has to be blocked. So of course you could build something that goes around all 4 edges. So that would have length 4. But it goes from one edge to some other edge, so you only need to cover 3 of the edges. Right? So that has length 3. Any other suggested solutions? Yes?
Can I draw it?
Yes. Yeah, why don't you draw it on the board? Okay, this is a great suggestion. And if you've studied soap films or anything like that, you probably think of a solution like this. What's new about this solution, it has some interior points here. These points are well known in classical mathematics and in graph theory and so on. A point like this, interior node, is called a Topological point. So what's new here, interior point, it's a 3-fold junction, trivalent vertex, 120 degrees between the points, has really nice symmetries and so on. This thing has length 1 plus square root of 3. This is not the best solution. Good try, close, but no cigar. Anyone see anything else? So it turns out this idea is good, putting in these interior points, but you can do slightly better, okay? Actually significantly better. So this is what? 2.73. You can put in one of these, you can put in 2 interior points, but differently distributed. So I know this very chart very well. One here that blocks half the diagonal. By the way, 2 diagonals is another solution. This one that you provided is better. You can have one interior point like that, and then another one, and you optimize where the other one is once you have a structure like this. And you can work out this angle here, 15 degrees. This is again 120, and so on. This is the other diagonal. This has length, a beautiful number, √2 plus √3 times. Now what's surprising about this? This original problem with the square has 8 symmetries, part of the dihedral group, 4-dimensional dihedral group. So it has 4 rotational symmetries and 4 reflection symmetries. 7 out of the 8 symmetries of the original problem are broken by this solution. It only has reflection symmetry about this diagonal here. So, if you try to utilize the symmetry of the problem, original problem, in the solution, you don't get anywhere near. This makes analysis complicated, and determining ground states in physical problems is essentially an analysis problem. You're minimizing some energy. So, this is very sobering. The other interesting thing is emergent topology in the solution. The solution has 2 disconnected components, this one and this one. You get a disconnected graph. If you're on this segment, there's no continuous line connection to this segment. So, symmetry breaking. Emergent. One of the things that appears in this. Now, what's a more typical setup we have in physics problems? Usually we have, so more generally, supposing we have a theory with some symmetry group, it's called big G, rotational symmetry. This will appear in the Hamiltonian. And the ground state, you can read vacuum here, same terminology, has symmetry H. There's some residual symmetry in the ground state. Generally, this can be smaller than the original symmetry G. This is spontaneous symmetry breaking. The space ground state manifold is, let's call it M. Applying symmetry group G doesn't change anything, but H is an explicit symmetry of the ground state. So H is the only thing that doesn't explicitly change this ground state. So we have to construct what's called a coset space, or mod out by the action of H. Everything by H doesn't change the ground state. Everything in G that's not in H does change the ground state. Is this clear? These guys see this kind of construction? Yes? No? Who's seen a coset space? Okay. But I think it's clear, right? So, we have examples of these kinds of spaces. This doesn't change anything. So, for example, if you had to take phi as a ground state. If you act with H, any element from this group H acting on phi, this is the same ground state. If you act with G on phi, and G is not in H, but it's in G, that gives you a distinct ground state. So if you sort of draw this,
What means distinct? I mean, is it same energy or?
yes, the energy is the same, but it's a different state. Physically and mathematically, a different state. A magnet polarized in this direction and this direction. And there's an infinite energy that separates them, which is why you have spontaneous symmetry. When the symmetry breaks, it can pick any direction in G. It picks one, leaves some symmetries invariant, that's H. And then everything, so that's the spontaneous symmetry breaking process. And a surprise that it can happen, but it does. Is that clear? Yeah. Yes, they're all ground states. So they all have the same energy. They're all minimum energy states. They're physically and mathematically distinct states. Physically different, they have different properties. They have a different magnetization, for example, or a different order parameter, S, that Jonathan introduced for liquid crystals yesterday. Or a different phase, or a different director. Yes. A different director, which we'll discuss, which is an orientation. It's more appropriately a different director. So, let's look abstractly first at the space. So the properties. Some very broad properties, first of all. Namely, we're going to look at what happens if we continuously deform this manifold of ground states. So we twist it and share it and bend it and so on, but we don't tear any holes in it. We don't do anything too severe to it. So this is encapsulated by the topology, the topology of this space M. And I'm going to, there are many measures of the topology, but I'm going to use one that's useful for characterizing a lot of defects in the system. Doesn't capture everything, but at least it's one of the simple ones you can think of, which is related to homotopy. Okay? But first of all, you can ask, so the first question is M connected? goes by the name of pi 0. So, i.e., what is pi 0? If this is trivial, this means it's connected. This means that, so here's generically what this space M looks like. Here's a point on M, this is a ground state. Every point on this manifold is a distinct ground state. And if it's connected, you can go from any one to any other one continuously. Here we had two connected components in the solution. We can't get from that right-hand thing to the other one. So it's not a trivially connected space. This is nicely illustrated by the easing model that Robin introduced. So, if not, we have a kind of very basic defect called domain walls. The terminology comes from 3 dimensions, and we'll see what kind of dimension these defects can have. Let's imagine that the symmetry group is Z2. So let's take spins that can just be up or down. The Drosophila of statistical mechanics, as Robin described it, the easing model, with up or down spins. The magnetized states, you need 2 dimensions or more to get some symmetry breaking for that state. 1 dimension, there was no ordered state, again due to defects. So 2 dimensions or higher, then we can have everything, all the spins up, or all the spins down. Those are 2 distinct ground states. So the symmetry group is Z2. This is the space just +1, -1. +1 is the identity if you want, -1 is the trivial element of this space. So what does it look like? You can have a region where all the spins are up, like this. Let's start in 3 dimensions. So this is a bulk 3-dimensional region, say inside this surface, sigma, where all the spins are up. That's a nice ground state. Everything is aligned. Remember, there's only up or down. But somewhere else, in the rest of the region, all the spins are down. They both, in each region, minimize the energy. But between them, we have this whole surface, in this case, where the spins are anti-parallel instead of parallel. So that takes us off the ground state manifold in this region. So this is the topological defect. So the dimension of this basic defect let's write it here. Dimension of this pi 0, let's call it, and I'll tell you what this means, is if we start in d dimensions, it's going to be d minus 1. Right? So if we're in 2 dimensions, it's going to be one 2-dimensional region separated from another 2-dimensional region like this, separated from another 2-dimensional region, this time by a line. So 2 minus 1 is 1. If we're in 1 dimension, you don't really have these states, but it will be a point defect. So the dimension of the defect depends on the dimension of the space in which you're working. Now let's look at more, well, another kind of defect that can appear in the system. And this time we're going to ask a slightly more subtle question about the ground state manifold. So this is 2, that was 1 up there. Domain walls, should be walls, lines, or points, depending on the dimension you're at. You say, is M simply connected? What does this mean? This mean, yes.
You have a question?
Oh,
Sorry, this pi 0.
Yeah.
I'm not sure. Is M connected? What is pi 0 of M? And then you
Yeah.
spoke about the dimension of pi 0.
Yes.
Defect is d minus 1.
Yes.
So what exactly
So-
is pi 0?
Yes. So this is just, this will be clear when I define this one here, why we're using pi 0. So you can just say, is M connected or not? And this is basically, this just measures the space of connected components. So if the space is, if it's connected, then pi 0 then is just the identity. If there's more than one connected component, they're related by some group, and that's pi 0. So right now, you don't know why this is called pi 0. I will explain that in a minute. A whole sequence of these pi's that will make this clear at that terminology. Just think of it as asking if M is connected or not. Forget the fancy terminology for the moment. And then I'll relate. Same here. First thing you can ask is M simply connected. So, what does this mean? Here's your space M. This means if you take 2 points in M, take a path between them, and then ask if that can be continuously deformed to any other path. Between these 2 points. So you take this, and then you sort of think of iterating it a little bit like this, iterating it a little bit like this. I know this, I'll draw this in white because the red doesn't show up very well. Move it continuously, just sort of slightly deforming this to this other curve. If M is simply connected, you can always do this. If M is not simply connected, then there are inequivalent paths going between 2 points. What we usually do is to take the initial and the final point to be the same. That's the simplest thing. So now we have loops. And by the way, to finish the answer to your question, this dimension is counting the dimension of the interface between the 2 connected components. So let's take the initial and final points to be the same. We have a loop now in the space. Every point on this loop is a distinct ground state. So imagine we start here and then we start moving. We do some Gedanken experiment that changes the ground state. So this is called the base point here. We would normally take this to be a uniform ground state. You know, it's a magnet, everything aligned in this direction. And then we can rotate slightly and have everything magnetized in a slightly different direction. And we go from here to here. And then we keep moving. We go around, we go on this big loop here. And then we come back to the same uniform ground state that we started with. So we could rotate a little bit this way and then come back. We could rotate far and out in 3 dimensions and back around. back to here as we go around. So this is a loop on the space of ground states. So we're kind of so then the question is, if this is simply connected space, we can just deform this, shrink this loop like this, shrink it down, shrink it down, shrink it down, until we do nothing. So we take our lasso and shrink it down till we've done no deformation whatsoever. If we've done no deformation whatsoever, we stay in the original ground state. Right? So, if the space is simply connected, you can continuously deform any, this is a kind of tour through any given point in here is a different ground state. We've sort of distorted the original ground state, gone through some operation as we go around and come back to the original ground state. If this is contractible, a simply connected space, we can contract that loop down to the no deformation whatsoever, the uniform ground state. That means there's no obstruction. No obstruction to having a just purely uniform ground state. Now, in contrast, and this is where the defects will come in, the next interesting class of defects, supposing this is not possible, right? Supposing that you can kind of lasso this space of ground state by wrapping a loop on it. You can wrap this loop or not. You guys know what a lasso is, right? Take a rope and you catch the neck of some animal, a bull, or a cow, steer, with a loop. And you wrap it around their neck and it cannot escape. Right? You shrink it down and capture the neck of the animal. Can we capture anything about this space if it's not contractible? Well, yes. So if it's not contractible, there's something that prevents this operation from occurring. So let's take one, this here. Let's take, I think most people can see one. Here. Let's take this space here. Let's take one big loop in this space. So here's M. Let's call this loop gamma. Let's take a non-contractible loop. So continuously, we cannot deform this loop down to a trivial loop that stays here at this ground state. What does this mean? Let's take the surface, any surface here, whose boundary is this loop gamma. Somewhere on the surface, there has to be a point that's not in the ground state manifold. So let's mark X here. This is a point on the surface. That's going to be the obstruction. We pull the loop down, and somewhere inside the loop, we cannot get past this point. Now, normally what happens, yes?
So you said that point doesn't represent a ground state, even though M represents the space of ground state?
Yes, so this is not on, this is any surface that's bounding sigma.
Okay, oh.
That surface can be anywhere. Gamma is on M, so here's M. Gamma is on M. And then we take any surface whose boundary is M. I mean, in the case where gamma is not contractible, I'm marking the point where continuously this has to break down. Normally what happens is the following. You have some kind of you can imagine some kind of effective potential for these kinds of systems, something like something like a Mexican hat potential or something like that. Okay? This represents, so at high temperature the system has maybe a potential like that with a minimum at 0. That represents no phase transition. And then at low temperature it develops some non-trivial minima with some order parameter like magnetization, or pneumatic order is non-zero, and this occurs at some non-zero value of the order parameter, and this represents the broken symmetry phase of the system. So the most common thing, so what I'm saying is, you cannot, at some point, for non-contractible space, there's an obstruction to contracting this loop all the way down to the beginning ground state. The most distinguished point is actually this one up here, where the order parameter is 0, where you're in the disordered phase, as Jonathan and Robin were describing. So the easiest thing to think about is that here, there's no symmetry breaking whatsoever. The order parameter is 0, and you're in the high temperature disordered phase, where there's no symmetry breaking. And you have the full symmetry group G. Yeah.
So for the Mexican hat in 2 dimensions, would that be not connected? And in 3 dimensions, you'd be connected, but
Yeah. Yeah. So this can describe many things. So we'll come back to that when we give examples. Let's get the idea here first. So somewhere inside here, there's a point that's not on the ground state manifold. Otherwise, I would just continuously deform down to this point here. Now I can do this one point. I can do this for any surface whose boundary is gamma. So I can take another surface coming out of the board like this. Somewhere on that surface is another point that's preventing the lasso from contracting down. Right? Everything is on M a priori, that's what you were asking. Everything is on M a priori. But if it's not simply connected, something has to break down. So I take another surface whose boundary is gamma, and I find a point here. That's the obstruction. That's, say, the high piece of the high temperature phase. And then I take another surface, there are an infinite set of them. It's coming out here, and somewhere on that surface there's another point. So if I connect all those points up, I have a line. Right? And in the center of that line, there's no symmetry breaking. You're in the high temperature, disordered phase. And everywhere else in the medium, you're in the ordered phase. So you're forced in this process, is what I'm saying. You're forced to uncover structures that's not uniformly ordered. It's an inhomogeneous state, and you have some excitation of the system with pieces that are not in the ground state. This is the topological defect. So here, this is a line defect, joining up all these lines, right, in 3 dimensions. You see that? Now, if this line terminates, so I'm lassoing my, oh, you can probably use this.
I have another question.
Yes,
So it's
good.
necessarily only one point for each surface?
No, at least one.
At least.
Yes. It can be more than one, but at least one. So here's my lasso. You see one surface is just plane, another surface bulging out here. It's at least one point here, another surface bulging out here. I join them all up, I get my line defect. For any surface, as I pull the loop like this, keeping that same bounding surface, something sticks in here. Prevents it from contracting. Otherwise it would be contractible. So that's the point I'm talking about. Some high temperature reaction. So I join all those up and I get a line. Any kind of line whatsoever. Now if it's freely terminating, as Robin was describing, I have this lasso, I can just pull the lasso off the end. So that's not a topological defect. That can be avoided. You can escape it. So this means it's either infinite in length, so I can't pull it off, or it's a closed loop, so that it gets stuck. Join this. In the end, I have a ring. I slide this all the way around the ring, or wherever I pull it. So this kind of construction, this uses, it's a more subtle measure of the topology of the space. This actually looks at, so these loops you can parameterize as points on a circle. I have a one-dimensional loop, beginning and ending at the same point. So what I have is actually, I'm looking at the space of maps from the circle to the ground state going forward. So I have basically phi of 0 equals phi of 2 pi. And phi of any angle in between is some ground state. And then I ask whether this is a non-trivial space or not. So the space of classes of these maps, this is Coulom's classes of these maps, this is called pi 1. This is pi 1 at the end. 1 refers to a one-dimensional circle. Non-contractible loops. So for non-contractible loops, you have non-trivial pi 1, and you have, in 3 dimensions, you have line defects. So the dimension of pi 1 defects is d minus 1, like we had before, minus 1. That one is the pi 1. So this is d minus 2. In 3 dimensions, these are line defects. If we're in 2 dimensions, now we have just a blackboard, and we can, all our surfaces have to be in the plane of the board, and so as we contract down, we just have that point that I described before. So in 2 dimensions, the pi 1 defects are point defects. Okay. Yes?
What guarantees this line to be continuous? Or, I don't know, the way you described it, it seemed...
That's part of our construction.
Okay.
We construct... The continuity has to do with deformation. So we build a closed loop on the surface, and then we take a one parameter, and then we start deforming it. That's the continuous part. So we just ask, can it be continuously deformed to a loop that does nothing?
No, but I mean, so then you take a different surface,
Yeah.
slightly bulged or whatever, and then you find another point, and now you're connecting up those 2 points.
Yes.
What guarantees that line to be continuous?
Oh. I don't need it to be continuous. I just need to show that there's a whole sequence of points that cannot be on the ground state manifold, in which the obstruction, and then I just connect them up.
Okay.
But it doesn't, yeah, it doesn't rigorously prove this is a nice, smooth 1D curve or anything.
Okay.
Right. For that, you would probably need some extra structure on the space. Good question.
But it would be connected at least.
Yeah.
You can't draw a line.
Yes.
It wouldn't jump.
Yes, that's right. There
But
cannot
you
be a
can
big
have
gash.
hints.
I
I
can
can
always
have hints
construct.
through, yeah.
Right. Wherever I want to point, I construct a surface that goes through there. Right. So these defects are very interesting, and let's do one generalization, and then give examples, because otherwise it gets very abstract. Actually, before I do higher homotopy defects, let's give examples from this one. So, first of all, let's do ferromagnetism. So in ferromagnetism, things are characterized by magnetization, which is a vector, also called polar order. Okay? So ground state has magnetization M, we can take it to be constant, but it's a vector. So let's quench deep into the magnetized state and just fix the value of the magnetization. This means in 3 dimensions, any direction from the origin gives a magnetized state. Direction going out from the origin will intersect some large 2-dimensional sphere at a point. So every point on S2, we discussed on Sunday, is a magnetized state. So this is the space of magnetizations. We have one here, ends there, we have one here, we have one here, we have one here, one here. Right? And going from one to another is a distinct ground state. By the way, at the beginning, we can have any rotation, SO3, we start with the Hamiltonian theory, any rotation gives a different ground state, but a fixed one has an invariance. You can rotate in a plane by any angle in a plane orthogonal to the direction of magnetization, and that doesn't change the ground state. So that's the space H. G is SO3, H is SO2. And SO3 mod SO2, that coset is just the space S2. And every point on S2 is a distinct ground state. Now, pi 0 of S2 is 0. It's connected. You can go from any point on the surface of the basketball to any other point. So no domain walls. Pi 1 of S2 is it simply connected? So I lasso the surface of a basketball. Any obstruction to doing this? None, right? None. Cannot lasso the basketball. So pi 1 of S2 is 0. No, let's call them line defects. No pi 1 defects. Let's do the liquid crystal case. Liquid crystals, we are now dealing with, even though one likes to introduce this director and so on that Jonathan introduced, you always have to stand on your head and impose this inversion symmetry. So a liquid crystal is characterized by an orientation, not direction. In fact, mathematicians call these line fields. You don't need this two-headed arrow. All you need is a line that indicates the direction of orientation. If we have an orientation like this, and we fix the magnitude, it intersects the two sphere at 2 points. One point here and at the antipodal point, or the north pole and the south pole. So, space of ground state manifold for liquid crystals, 3 dimensions, is S2 modeled out by this inversion, Z2. This identifies this point and the antipodal point through the origin on S2. This is an orientation. Mathematicians call this projective spaces. We have rays, or orientations, rays like in polymers. Projection. Now, pi 0 of this space. So this space is called RP2, real projective space. Pi 0 of this space, RP2. It's still 0. It's connected. Let's look at pi 1. So here's this RP2. Let's take loops based at the north pole. If we do any kind of small loop, we don't know that we're on RP2. It just looks like we're on the surface of a sphere. We don't get to the antipodal point. S here. N and S are the same point. So it kind of looks like might be contractible until we do the following thing. Let's take a loop that goes and ends here. Is this a closed loop? It is, right? Because N and S are the same. It is not closed on S2, but it's closed on RP2. Now if you have this loop, this big excursion here, you cannot contract that down to this trivial one here without breaking it off S2 here. You cannot pull it back. So that is an example of a non-contractible loop on RP2. So the liquid crystal case immediately has new topological features to ferromagnetism. So the liquid crystal has pi 1 defects. So what do they look like? You've already seen them. Let's take 3 dimensions and let's take a cross section through that. So we're looking at a 2-dimensional piece of it. So the defect will look like a point in 2 dimensions, and then we join them up and we get, they're called disclinations for liquid crystals. We're going to have a point here, which is a high temperature, say, isotropic phase. And as we go around, let's look at a non-contractible loop. Somewhere it's going to be uniform, say out here. And as we go around this loop, we have to wind from this direction. Well, actually, let me work this way. We start with direction out here, an orientation out here. As we go around this point, we have to wind from the north pole to the south pole. North pole has an orientation like this. The south pole has just the reflected orientation. which is the same. But we don't want to be the uniform ground state is everything lined up like this. So let's take a configuration, two-dimensional slice, goes here. It's got to wind 180 degrees to get the inversion. So as we go halfway around, it has to wind 90 degrees. So it's going to look like that over here. As we go a quarter of the way around, it's going to be wind 45 degrees. As we come around here, another 45 degrees, and back to here. Well, this is what it looks like. So this is the configuration that you've been seeing. And then I can join this down, say uniformly if you want, in the z direction, but go on to infinity to get a line defect. So let's draw it again. Here's the defect. Here's the direct configuration in the neighborhood of the defect. Out here, it's just uniformly oriented this way. Way out here, it's uniformly oriented 90 degrees with respect to that. And we cannot continuously deform this kind of configuration to the uniform one because there's a point here that obstructs it. So what I will do next time is tell you now how to count what's the measure and how to count the topological strength of this defect and relate it to this pi1 space, and do it in 2 dimensions and 3 dimensions compared to vector order, and then tell you about high dimensional. So spaces can have non-contractible 2 spheres and non-contractible 3 spheres in them. And that gives you higher defects, pi2 and pi3 defects, which you've already seen, monopoles and this hot vibration. Okay? Question?
Thank you. Are there questions for Mark? No, I have a question.
Yeah.
Okay. So with this example of the liquid crystal in 3 dimensions, right? And so you have your non-contractible loop, which starts at the North Pole and goes around to the South Pole, and that's equivalent to the North Pole. Right? So how do you know what states it encloses, right? At some point you sketch the states that are enclosed by that loop. So how do you know what's enclosed and whether that includes the isotropic state?
You don't, but you know, you know there exists a configuration that's not contractible to the uniform configuration with an obstruction. So you don't know in detail, but you can, here's an explicit realization of such a such a non-contractible loop on the space. Here's the North Pole, and here's comes back, equivalent point here. But you haven't stayed. You've gone on this big loop. So you don't know a priori, but you can realize what the non-contractible loops are.
I guess the reason for asking that question is if I wanted to know whether the core includes an isotropic region or if it could be something completely different, like biaxial.
Right. The construction doesn't tell you that. It only tells you there has to be something off the nematic ground state. It's only that that this is kind of the simplest realization. What happens is going around. So if you go, so what happens is supposing here's a big loop around here. But let's imagine this operation of shrinking the loop as we've been describing, right? Shrinking the loop means, I'll draw it in red even though it's hard to see. Here's your big loop around, and here's the point inside. Let's take a smaller one. Kind of the same operation at one. Let's take a tiny one going around here. The director still winds 180 degrees over a vanishingly small circumference as it goes around. So in the free energies for these theories, you have gradients of the director. Those are going to blow up as you go down towards here. So both mathematically and physically, it's reasonable, instead of having a singularity, which is a diverging derivative in the theory, you replace it by a zero. So it's not really a singularity, it's a zero of the field. The orientation is not defined. So, but zeros are important, well, they're kinds of singularities, but important structures in the field. So, but it could be something else. The construction only tells you it's something not uniform in matter.
Mark, I have a question for you too.
Yes.
Aside from using these methods to visualize and understand topological defects,
Yes.
on an operational level, if I give you a vector field defined at each point in a cubic lattice, and I have 2 angular degrees of freedom, so I have this pneumatic director essentially at each point on a 3-dimensional lattice, and say in the middle of a simulation. Can you use these techniques numerically to identify and classify the defects?
Yeah, I mean you can. So you have to discretize it, but you can take your discrete lattice and measure the winding numbers and label. So you had, for example, you painted the structures around your defects, but didn't label, at least in some cases, didn't label them. But you can label the core of the defect and the strength of the defect by this counting, by measuring the winding.
Okay, the fact that the pneumatic director doesn't have a definite sign
Yes.
means you have to make some decisions as you circle anything about how you actually copy.
So you should never, strictly speaking, should never assign any vector order in that case. Always deal with these line fields. These are fundamentally different systems. If you put on the vector order, you're asking for trouble. That's the only reason you have that ambiguity is you impose a fake structure on it. So these are the best examples that take your fingerprints. Have a look on your fingers right now. I bet everyone can find a 1/2 defect.
You don't have any twins.
Raise your hand if you don't. Raise your hand if you find it. Find it? And then you'll find -1/2 also. There's no vector field anywhere here. These look like ridges, right? You can also call this ridge systems. Topographic lines. They don't have a vector field on them. So really, the better way to work with in this case are these lines. But it's complicated. You want to put vector fields on these things. You want directions, but it's not. It's an orientation. It has this fantastic structure. By the way, there are also, so typically because of boundary conditions and so on, bulk of defects occur on the whole hand in the gaps between fingers. So there are actually in excess of minus defect on each gap between fingers. So if you have D fingers, there are D -1 defects in the space between, which is if you have dermatoglyphics, studying fingerprint patterns. This was studied by Lionel Penrose, Roger Penrose's father, and Roger Penrose himself. But so identify those defects on your fingerprints.
Can you comment on how?
Does that sort of answer your question?
Yeah, I was going to say the FBI has some system for looking at handprints of thousands or hundreds of thousands or millions of people,
Yes.
and then unambiguously identifying individuals from fingerprints. They must use some of these methods.
Yes, I think so. And there are also people in the medical industry are interested in whether certain pathologies are associated with certain defective structures in the fingerprint.
So there we have some alternative careers with the FBI. Robin, I'm afraid we have to move on to our next speaker here, who is somebody that you may have seen on Facebook. So.